In this video, we'll look at what is perhaps the most common use of R by most social scientists, and that is loading, looking at, and analyzing data. Now, there are a lot of different ways to load data into R. We're going to look at one of those today, and that is loading a data set from a different statistical software, in this case, Stata. To do this, the first thing we're going to need to do is install a package. A package is a user-written set of commands that add on to R. Usually packages don't come automatically in R, although there are some. Most of them you need to install and then load on your own. The package we're going to look at here is the foreign package. The foreign package allows us to import data from a lot of different popular statistical softwares. Stata is one example, but others include SAS and SPSS. There are a number of different ways to install a package. One way is simply to type install.packages and then the name of the package inside the parentheses and inside quotation marks, as I have here. If I run that line, R asks me to select a crayon mirror. This is a site from which I'm going to download this particular package. And here it asks me to type in a number, which I do. Once it finishes downloading it, it leaves you a message saying that the downloaded packages are in a particular file and you're ready to go. Now, installing a package is one thing, bringing it into your current R session is a different thing. For this we use the library command. When I type library foreign, as you see here, that actually brings the foreign package into my current R session. So library and then the package name is a command that you need to do each time you want to use that package in a given session. But the install.packages command is something you only need to do once. Now, once I have the foreign package loaded, I have access to a command called read.dta. This is the command that is unique to the foreign package that allows us to bring in Stata datasets. The example we're going to work with today is a dataset on crime in the American states. I have this file saved as crime.dta on my desktop, and so inside the parentheses of the read.dta command, I'm going to write in quotations the file path for that particular dataset. And I'm going to call that dataset an object called crime. Now there is another way that I could have done this. I could have used the setwd command, that stands for set working directory, and typed in the file path of the directory, and then I could have used the read.dta command and simply given the name of the data object. Both of these options that I have here do the exact same thing in slightly different ways. Now there are lots of different ways we can think about working with these particular data or taking a look at them. If you want to see all of the variables listed in the dataset, use the names command. And as you see here, this prints out the names of the different variables in that crime.dta file. If you type summary and then the name of a particular variable, you'll get a summary, as we saw before, because remember, each of these variables is simply a vector, and so R treats it that way when you use the summary command. Same thing if you wanted to use the mean or the max or the min command. Now, there's some important notation that I have on this line that you should be aware of. To refer to this specific variable, %male 14 to 24, notice that I used a $sign here right after the name of the data object. That's how you refer to specific variables in a data set. Type the name of the data set, then the $sign, and then the name of the variable. This may seem a little bit annoying at first, but it's actually very useful because it allows you to have multiple data sets in R's working memory at any one time. Remember, this particular data set is called crime, but I could create another data set using a different file that I call a different name, and I can look at objects inside each of those data sets all in one R session. R can do a wide variety of statistical analyses, including multivariate models. For example, to do ordinary least squares regression, the command is LM, or linear model. The syntax for OLS and for other types of models is inside the LM command you put the dependent variable. So in this case, our dependent variable will be crime 1960, which is the per capita crime rate in a state in the 1960s. Then you write the tilde to separate the dependent variable from the independent variables, and you list all the independent variables you want separated by plus signs, and that's what I have highlighted here. And then we need a comma, and there's an argument called data, and in the data argument you simply list the object name for the data set that you want to use. Again, this shows R's capability of using multiple data sets in one session. If I had another object that had a data set, I could put that in that argument and use that one. For now, I'm going to run this model. I'm going to call this model OLS.1. Now, if you simply type the name of the model object that you created, all that you get essentially are the coefficients. But what if you want more than that? Well, we saw the summary command earlier. We can use that summary command again when we use models, and it's going to give us a summary of that particular model. So if I type summary OLS.1, now I've got a summary of the residuals, I've got the coefficient estimates, I've got standard errors, t-values, and p-values. Additionally, I get some information down here, including the residual standard error, the R-squared values, and the f-statistic. Now, you may remember for when we use the names command that there are more variables in this crime data set than I showed in this first model. Let's say I wanted to include all of the variables in this data object called crime. One very short and easy way to do that is to type the dependent variable, the tilde, and then a period. That will put all of the variables in that object on the right-hand side of the model. So I'm going to run that, but I'm going to name it something different. In this case, I'm going to name it OLS.2. So notice that I still have the object OLS.1 in the working memory of R, but now I'm estimating another model and assigning that to a new object name. And again, I can use the summary command to print out a summary of those results. And here we have all of the variables in that data set on the right-hand side of the model. Now, another useful feature of R is that it's very easy to refer to specific attributes of a given model. For example, let's say I wanted to create a vector that was just the coefficient estimates from a particular model. If I type OLS.2, or the name of the object, then $, and then coef, C-O-E-F, that will produce a vector of the coefficients, which you see here. In a similar way, we can say the OLS.2, then $ residuals. That will produce a vector of all of the residuals, so one for each observation. Notice that we've used the $ notation to do this. This is similar to up here when we looked at a particular variable in the data set. In this case, we're using the $ notation to refer to specific objects in the model estimation. We can also use that $ notation to pull different elements out of the summary command. So notice here I'm typing summary of OLS.2, but then I'm typing a $ and then adj.r.squared. This is the means of pulling out the adjusted R squared from that particular model. which we see here. To get the variance-covariance matrix of a particular model, use the command vcov, and inside the parentheses, put the name of the model. Here we have the variance-covariance matrix. To get the standard errors of the model, we can take the square root of the main diagonal of that variance-covariance matrix. So to do that, I'm going to use two commands nested in one another. First one is going to be diag, D-I-A-G, and inside the parentheses I put the name of the particular matrix that I'm working with, so in this case the covariance matrix. The diag command produces the main diagonal of that matrix. Then around that I'm going to wrap the command sqrt, which stands for square root. So I'm taking the square root of the main diagonal of the variance-covariance matrix. And that produces the standard errors of the coefficient estimates. Another nice feature of R is that it can do on-the-fly interaction terms. And what I mean by that is you don't need to create a separate variable that is the interaction of two different variables. For example, here I've created another object called ols.3, which is the same right-hand side variables as ols.1, but now I'm adding this additional term, wealth times inequality. So there's my interaction term. And I'm going to run that code and the summary command. And notice that it created this additional term down here, wealth times inequality, that is the interaction term. R has the capability to do a wide variety of statistical models. And another example of that is its capabilities for generalized linear models, or GLMs. These are things like binary outcome models, count outcome models, and other similar models. Let's look at a quick example with logit. So to do this, the first thing I'm going to do is get some data from the Zelig package. So notice I'm typing library Zelig, that's the package that I want. And if you haven't already installed this, then you would need to type install.package and insert Zelig. Now the data that I'm going to use are data on voter turnout, and they come from the 2000 current population study, which is part of the census. To get these particular data out of the Zelig package, we use the command data and then type the name of the data object, which in this case is vote income. After doing that command, we've now got the vote income data loaded in the object vote income. To do a logit model, the command that we need is GLM, which stands for Generalized Linear Model. And we type the dependent variable, which in this case is vote. That's a 1 or 0 variable, whether or not a person voted. Then the tilde, and then our independent variables, just like we saw before. But now we need to add in some additional arguments to tell R to estimate a logit model. And that is the family argument. To do a logit, we type family equals binomial, and then in parentheses we type length equals logit. If we typed length equals probit, we would get a probit model. And then we type data equals and the name of our data object, which is vote income. Otherwise, this process works exactly the same as we saw before. So what we see here again is a summary of the logit model that we just estimated. We've got the coefficient estimates, standard errors, z-values, and p-values. And additionally, down here we get some model fit information, such as the deviance of the null model versus deviance of the model that we estimated. It also produces the AIC value. Now let's say we wanted to pull out various elements from this logit model, such as the coefficients. We can do that in the exact same way as we did before. the name of the model object, in this case logit.1, $coef, or let's say we wanted to get fitted values, that is, in this case, for a logit, predicted probabilities. We type logit.1, $fitted.values, that's what that'll produce. We can also pull out the value of the AIC by typing the name of the model object, then $, and then AIC. And we can get the covariance matrix of the coefficient estimates and standard errors just as we did before, that is with the vcov command. The standard errors, again, square root of the diagonal of this matrix, which is the covariance matrix. As I mentioned before, there are a lot of different models that you can estimate with R, but nearly all of them are done in this same syntax and structure. Additionally, nearly all of the ones that you can do in R have this same setup for extracting various elements from the model object. So I encourage you to explore different uses of the GLM and LM command, as well as other packages that provide more specialized models. Now in the next video, we'll talk more about R's capability for producing graphics.